Hello FYP moderators, my name is Akmal Zohairuddin bin Muhammad Idris and I'll be presenting my final year project titled Design Optimization and Performance Investigation of a Rooftop Solar Fan Ventilator. This project was supervised by Professor IR Dr. Chungwen Tong. So for the introduction, ventilation systems are critical for indoor comfort, especially in tropical climates where temperatures and humidity are high. Applications include warehouses, attics, and residential rooftops. Solar-powered rooftop ventilators provide a sustainable passive cooling solution using renewable energy. However, many existing designs show poor airflow and insufficient protection against rain, debris, and insects. This study aims to optimize the ventilator design by improving airflow efficiency, structural durability, and environmental resistance using computer-aided design, CAD, computational fluid dynamics, CFD, and finite element analysis, FEA, and experimental testing. So for the methodology, the ventilator was designed in SolidWorks focusing on streamlined airflow and improved rain deflection. As shown in Figure 1, the final model features two angled vents, reinforced structural supports, and a protective mesh placed downstream of the fan. This design became the foundation for simulations and physical validation. So for the CFD setup, CFD simulations were run in ANSYS Fluent on 4 models, the current design, a previous prototype, and 2 commercial square and circular profile models. The setup used a steady-state pressure-based solver and with a realizable K-epsilon turbulence model. A rotating frame of 1,200 RPM was applied, which was referenced from previous experimental studies. A mesh sensitivity analysis was also conducted to ensure result stability. As shown in Figure 2, mesh refinement achieved only a 3.75% variation, confirming simulation accuracy. So for the FEA setup, for structural evaluation, ANSYS static structural was used to simulate combined wind loads. External flow velocity was set at 32.6 meters per second based on Malaysian wind design standards, while internal flow velocity averaged 3.16 meters per second taken from CFD results. Pressure fields from the CFD simulations were imported directly into the structural solver. The ventilator was modeled using aluminium with a yield strength of 2.8 times 10 power of 8 pascals. The analysis outputs included von Mises stress, total deformation, and the factor of safety FOS. So for the experimental setup, the prototype was tested in a controlled lab rig. 4 500 light bulbs, 500 watt light bulbs were used to simulate solar power. This setup aimed to replicate fan speeds as close to 1,200 RPM as possible, aligning with the CFD rotational domain. An anemometer was used to record inlet air velocities across 5 radial points. The mass flow rate was calculated using the measured area and velocity. As we'll see next, the experimental values showed very close agreements with the CFD results, reinforcing the model's reliability. So for this CFD and experimental results, the CFD predicted mass flow rate for the current model was 743.3 CFM. The previous prototype achieved 696.6 CFM, and the square profile commercial model 663.8 CFM, and the circular profile model 454.5 CFM. Figure 3 illustrates the velocity contour of the current design, showing the smooth upward flow with minimal turbulence. Experimentally, the current model reached 724.4 CFM as seen in Figure 4. This results in a 2.95% error, which can be attributed to minor differences in fan RPM and between simulation and real-world testing. Even with this difference, the error is very low, confirming high reliability of their simulation results. So, for the structural FEA results, the FEA results are shown in Table 2. All models successfully withstood the applied wind loads. For the current model, von Mises stress was 3.48 times 10 power of 7 pascals with a factor of safety of 8.05 and a maximum deformation of 4.43 times 10 power of negative 4 meters. For comparison, the previous model recorded an FOS of 9.43 and the square profile model 15.30 and the circular profile model 58.95. All models recorded FOS values greater than 8, confirming they are structurally safe under both internal and external aerodynamic pressures. While the circular model shows the highest FOS, its airflow performance was the lowest, making it impractical. Figure 5 shows the CFD pressure field used for loading, and Figure 6 shows the resulting structural deformation, confirming that no structural failure occurred in any of the models. So for the rain and insect resistance test, the rain resistance test was conducted by spraying 6 liters of water at angles ranging from 0 degrees to 90 degrees from horizontal. The ventilator showed complete resistance at angles from 30 degrees to 90 degrees. At 30 degrees, the ingress was 3.7% and it increased up to 14.7% at a 0 degrees horizontal spray. This highlights the need for improvement in vent geometry for extreme wind-driven rain scenarios. Experimentally, only the current model includes a protective mesh to prevent entry of insects such as roaches and lizards during periods of non-operation. The mesh has proven effective, while the other models had no such protection and were fully exposed to external contaminants. Figure 7 shows the rain resistance experimental setup used. So for conclusion, the optimized ventilator achieved the highest airflow performance at 743.3 CFM, with experimental validation at 721.4 CFM. The simulation error was only 2.95%, confirming the reliability of the CFD approach. Structurally, the ventilator remained safe under both internal and external pressures, with all designs recording factors of safety above 8, and the rain resistance test showed good protection at common rainfall angles, while the inclusion of a protective mesh ensured reliable insect and debris resistance. Overall, the new design demonstrates strong potential for long-term use in the tropical rooftop ventilation applications. Thank you very much.